That's right. Okay, so again, the pair distribution function can be used to describe liquid crystalline materials. Again, luckily, there are other descriptors that can describe these structures even better, and that can actually tell you what is the difference between the nematic and the smectic phase, etc. And we will define them as the orientational order parameter S and as the translational order parameter sigma. So we will see that the orientational order parameter S is relevant for nematic, but as soon as you start to talk about the smectic phases, it becomes, this translational order parameter becomes more relevant. Okay, so we will define this orientational order parameter S in 2 steps. So first I will describe you how is this defined in 2 dimensions, simply because the math is a little bit easier and simpler. And then I will show you how this is done in 3 dimensions. Okay, so we are starting with the idea is that you have individual molecules in a liquid crystalline form. And again, each molecule has its own direction, which I will describe as pi. And this particular material also has a director, which is, let's say, in this direction. And the angle between the pi and n will be the angle theta I. So each molecule within the liquid crystalline material can be defined in this form. So then I can define an orientational order parameter S as follows. First I will define it, and then we will see that it has very specific characteristics that are very useful to describe this. But the definition of the orientational parameter S is 2 times the average over the volume of n times pi squared. And these brackets indicate that I'm averaging over the volume. What that means is that I'm averaging this value over all of the molecules within the crystal, and then minus 1. So first we will calculate what is this n times pi. It is equal to the magnitude of n times the magnitude of the pi times cosine of the angle theta I. And by the definition, the length of these vectors is equal to 1. So what is really relevant is simply the orientation. Their magnitude is equal to 1. And for that reason, this results is in cosine theta I. So then I have to calculate what is this S. So it will be 2 times cosine squared of theta I, which is average over the volume, minus 1. And then I can calculate what is the average orientation of, or what is the average value for this cosine squared theta. And for that, I need to know what is the distribution of the orientation of the molecules. So, for example, if I define cosine squared theta over the volume, this will be equal to the integral from 0 to pi of cosine squared theta times the probability that a certain molecule has an orientation in a certain direction. And I will describe this in more details right now. That is integrated over all of the angles theta. And this theta can go from 0 to pi. And then I'm averaging, or I'm normalizing this over the integral of 0 to pi of the probability that you will find a certain orientation that is integrated over the angle. So this will be just a simple definition of how I can calculate this average value of this equation here. The question is, what is this probability that you will find a certain orientation of a molecule? In liquid crystalline materials, as we mentioned last time, this probability would look somehow like this. So if this was the probability for the liquid crystalline material, how would this look like? So this is the probability that you will find an orientation of a molecule in a certain direction. How would this look like? We talked about this last time. Yes? Did you raise your hand? No? Yes?
So I guess you have a peak, in the middle of the peak would be the n direction.
That's right.
And then it would just be like a Gauss distribution.
So there would be a peak that is centered around the orientation of the director for that crystal. What that means is that most of the molecules have the orientation of that director. Some of them can deviate from that. And again, the ordering of how well they are oriented simply is described by the width of that particular peak here. So if I, for example, have a solid material, okay, if I have a solid crystal, and if I look at this equation, what would be this probability for a crystalline material? So I'm looking at this particular case here. What is this probability of theta for this particular case? Maybe some, yes. It would be one discrete point. What that means is that it would have value of 0 for theta that is different from 0, and where 0 will be the direction of the director, or the orientation of the molecules. And it would be 1 for this angle equal to 0. And if I calculate then this cosine squared theta, and if I average this over the volume, this equation here would be simply equal to 1, and therefore the S, or the order parameter, would be 2 times 1 minus 1 is equal to 1. So what that means is that in the solid crystalline material, this particular equation, how we defined it, has the value of 1. Okay, so I can calculate this same equation for a completely isotropic liquid. So I'm looking at this particular case. So if I'm looking at the liquid, so this P of theta will be what? Maybe this part of the classroom? Yes?
Sorry, what you just wrote.
Oh, sorry. So the question is, what is the probability that you will find a certain orientation in a completely isotropic liquid? What is this P theta? Yes? It will be constant, right? So what that means is that the orientation of the molecules is completely uncorrelated. What that means is that the probability that you will find an orientation of the molecule is equal for all of the angles. So this would be a constant. So if I calculate the value for S in this particular case, oh gosh, so this would be 2 times, I will calculate I can actually write this down. So the cosine squared theta, that is average over the volume, would be 1/2 of pi over pi, and the value would be 1/2. And when you calculate S, it would be 2 times 1/2 minus 1, and it would be equal to 0. So what we just calculated is that if you define the order parameter in this particular way, it has 2 very distinct values or magnitudes for the crystalline material and for the liquid. So for the solid, for the crystalline material, S will be equal to 1. For crystal, it will be 0 for liquid. And for liquid crystalline materials, it can have any value in between. So if you have this order parameter, and if the order of this is between 0, is between 0 and 1, this is liquid crystal. Yes?
So how is this different from director? Like, how are they related?
So this order parameter itself is defined by the director itself, right?
So is director considered a separate descriptor, or do you exclusively use S?
So the director itself is a descriptor that will tell you what is the orientation of that particular liquid crystalline in that particular area of the crystal. This particular order parameter will be used. We will see that it can tell you whether the material is liquid, whether it's crystalline, etc. Right? And we will see that it can tell you whether the material is nematic, smectic, etc. So we are just refining the level of the description. So the director itself can certainly be used, but it describes only a certain feature of that material, right? It describes the orientation of the molecule in a certain direction. This tells you even more than that. This tells you whether the material is completely liquid, whether it's crystalline, and the magnitude of this tells you what is the ordering. Because the nematic phase, it can be more or less ordered, right? So the magnitude of that will tell you what that is. And you cannot distinguish that simply from the director, right? Okay. Okay, so this was the case for a 2-dimensional crystal or liquid crystalline material. So we defined this in this particular way. So we can do the same exercise in 3 dimensions. The thing is a little bit more complicated because now you have different angles. So this is the orientation of a molecule, and this is the director. And if I define this as a z direction, Then, and this will be then y, and this will be x. Then, in principle, this theta I is still here, but I do have an additional angle, which is simply the projection of this individual direction of molecule in the xy plane, and I will call this phi. So in two-dimensional case, we just cared about one particular angle. In 3 dimensions, this molecule, in addition to this orientation, can have any orientation like this, right? So this will be described by this phi I. So in that particular case, the order parameter, and again, the description or the probability that you will find a molecule in a certain angle is again centered, and it's positioned at a certain set of theta and phi values that are describing the director itself, right? So this peak here again would be for the combination of these angles that are telling you where this director is. So I can define the order parameter in this particular case as S equal 1/2 of 3 times n times pi, that is squared and then average over volume minus 1. And again, in this particular case, this will be equal to 1/2 of 3 times cosine squared theta, which is average over the volume minus 1. And then again, I have to calculate this cosine squared theta, that is average over the volume. And in this particular case, I have to average this over all of the solid angles. And then the solid angle, d omega, will be equal to sinus theta, d theta, d phi. So just simply plug this into the equation. So this will be from 0 to pi, which is the theta angle, 0 to 2 pi's, cosine squared theta times probability that you will find this molecule in this certain orientation. So this is the p theta, p phi, times sinus theta, d theta, d phi. And we are normalizing this to the probability that you will find a molecule in general. So this is the integral from 0 to pi, integral 0 to 2 pi, p theta phi, d theta, and d phi. Okay, so you seem to be confused. Is everything okay? Yes.
Is the one inside of the parentheses or outside? Because I have parentheses on the
It's
left.
outside.
Outside?
Actually, let me verify. Yes, it's actually, I'm sorry, it's inside. So again, the way how this is defined, there is a specific reason why it's defined like this. Again, it will have a very specific values for the crystalline and for the liquid phase, and anything in between will be for liquid crystalline phase. Again, so the reason why these numbers 3, 1/2, and -1 are defined is to give these values at the end. So if you do calculate this, then the S value for crystals in 3 dimensions will be 1. It will be 0, like in the 2-dimensional case for liquids. And it will be in between for most of the liquid crystalline materials is typically between 0.3 to 0.7 for liquid crystalline materials. But again, anything in between, in principle, can be called a liquid crystalline material. It happens to be that for many of them, it's in this range of values.
Should there be a sign data on the bottom?
There should be, and you're right. Thanks. So, again, we won't go through the entire math. You're welcome to do it at home. It's a relatively straightforward math. But the take-home message is that this is the result. And when you calculate this order parameter and when you plot it as a, for example, function of temperature for a given material, it would have this general form. So what that means is that if you have a crystalline material and it's at low temperature, when you switch to the liquid crystalline form, which is in this particular case nematic, then again the value will be close to 1 but less than 1. And then as the temperature decreases, this value goes down. Why does it go down? I'm in the liquid crystalline phase, so this is not a fixed value at for all of the temperatures. Why does it go down? At the end, I will hit the liquid crystalline phase, which is, liquid phase, which is highly isotropic. Right? So the question is, what's the meaning of the magnitude of this order parameter. Why does it go down? Okay. So when you start at relatively low temperatures, although you hit a liquid crystalline phase, you are relatively highly ordered. So the magnitude of this order parameter will tell you what is the level of the ordering. When you increase the temperature, as you mentioned, it becomes less and less ordered, and this magnitude goes down. Eventually, you lose completely the information about the ordering, and you hit the value of 0, which is for liquids. Okay, so that certainly can be used for nematic crystals. For the smectic crystals, again, it can be used, but because there is an additional level of the ordering, we can define yet another descriptor that is quite useful. So for example, when I plot the probability that you find a molecule at a certain distance z along the layered smectic crystal, then this probability would look somehow like this. So the probability that you will find a molecule would be centered around the center of the mass within this layer. So there is high probability that I will find a molecule here, and then it drops down very quickly. And then it's again layered periodic function. So this periodic function then goes like this, right? And it's layered. And in this particular case, we can define yet another descriptor, which is called translational order parameter. And the name itself tells you that it gives you the information whether there is translational order. In the nematic phase, we did not care about this because there was no translational order, but in the smectic crystals there is. So again, how do you quantify this? So again, these layers can be very well ordered, but there can be some mismatches between them. How do you quantify this? So this particular value will be defined as sigma Sm is equal the average over the cosine 2 pi z over A, that is average over the volume of the crystal. And again, this can be written as an integral from minus a half to a half cosine 2pz over A, probability that you will find a molecule at a certain distance z times dz. So you're integrating over the distance. And again, it's averaged over the minus a half to a half pz dz. And again, when you calculate this very carefully, you will see that the value of this order parameter is equal to 0 for nematic crystals, and it is finite number less than 1, but is different from 0 for smectic. Again, the reason and the way how this is defined is simply to distinguish if you do have any ordering in the liquid crystalline phase, right? In the previous case, the S ordering factor would simply tell you what is the orientational order. To quantify this potential translational order, you have to define this number here. So when you look at more carefully, then there are different types of descriptors. So the smectic, so the order parameter, the smectic translational order, and at the end, the smectic phase order parameter can be described as the product of them. And if you simply plot this, it would look somehow like this. And again, based on the magnitude and how this particular shape looks like, you can tell something whether there is ordering or not. For example, for the translational ordering parameter sigma, this number goes to, it starts from a certain value, then it decreases because you're losing the translational order, and then it drops at this particular temperature, where the material goes from what to what? What is this? This Tc. What's that number here? Yes? It goes from smectic to nematic phase, that's right. So basically, there are different ways how you can describe different features of the liquid crystalline materials, and they extensively